Hello and welcome to our next lesson. Today we are looking at sine law and we are going to be investigating sine law using technology and also applying it to acute triangles. And remember, acute triangles are those in which all the angles, all the interior angles are acute angles, which means they are less than 90 degrees. So previously we looked at Pythagorean theorem and trigonometric ratios. Now, those ratios only apply to right triangles. And as we saw with the example with the triangular shaped garden, we weren't able to use the trig ratios right away because we didn't have a right angle. And we had to draw the height which produced the right angle. And then we were able to apply the trig ratios. Now, when it comes to acute triangles, we want to be able to solve also for the side lengths and the angles, and we will be using sine law and cosine law. So you can try this following activity. You can use GeoGebra geometry, so it is linked here for you, and this allows you to draw a triangle and use the measurement tools to measure the side lengths and the angles in order to determine the answers here. You can also draw this by hand, but it will be an extra step where you have to use manually yourself a ruler and a protractor to determine the measure of the side lengths as well as the angles. So to start, draw any acute triangle and label the vertices A, B, C. So you would draw any triangle here. Maybe let me do this. Okay. And I'm also going to do maybe a different color. Oh, okay. So let's say this is A, B, and C. And now label each of the sides opposite to the vertex with the lowercase letter. So if you are using GeoGebra, you may not be able to label it directly as long as you just know that the opposite side lengths are the lowercase. And maybe let me even, okay, we're gonna do here. I'm gonna use a darker color for this just because the C's kind of look similar. Now, then you're going to use the tool, or again, if you're drawing by hand, to measure all of these side lengths and these angles. So if you are using the GeoGebra tool to measure this angle, you would select the measure angle option, and then you would select BAC to form this angle here, and it will show you the measurement there. And you will do that for all of these side lengths and the angles. And now you're going to pick any of these vertices, A, B, or C, and you're going to evaluate the ratio as such. You are going to take the side length that's opposite. So let's say we pick A. You are going to find A and sine of A. Or if you are using B, it would be B over sine of B, or C would be C sine of C. And that's exactly what is step 5. So you do have to find those anyways. And you can now even try with any other, you can just draw another acute triangle and try this again to measure all the angles and the side lengths, especially if you are using a geometry tool online. That should be really easy to do. And I want you to think, what do you notice and how are the ratios connected? And you should be able to see that in fact all of these three ratios are the same. So in an acute triangle, any side length, the ratio of that side length to the sine of the opposite angle will be the same for all of the side lengths and their opposite angles. And this is actually precisely the sine law, which is helpful when solving acute triangles. So now using these ratios, oh, and the fact that these are equal, so there's equality here, how do you think sine law is going to help us when it comes to solving acute triangles? And solving a triangle is just finding all the different side lengths and the angles. So consider you have any side length or any side length A given to you, and perhaps you even have A and B. and you're also told angle A, and you want to figure out what angle B is. How can you use this to find angle B? You would pretty much set up this part of the equation. So A and sine of A you should have, and B is also given to you, for example, and we want to figure out sine of B. And so you would be able to, again, write out this ratio and rearrange to find sine of B is equal to a value, and then taking the inverse sine, you should get B is equal to the angle that would be over here. And of course, you can do that for C as well. So let's look at now our sine law. So sine law is, again, for just acute triangles. So all of these three angles are less than 90 degrees. And sine law tells us that any side here, so A, the ratio to the sine of the opposite angle is equal to B, the ratio of B and the sine of its opposite angle equals to C and the sine of its opposite angle. And in fact, because these are ratios, we can also say that the reciprocals are also equal. So here I've just found the reciprocal of each of these ratios, and of course, this is also equal. And that's why, if, for example, if you're solving for B itself, maybe you start with this, so then your rearranging is a little bit easier. You just have to multiply by B there. So let's start with our first example here. So here we have an acute triangle, and we're just asked to use the sine law to find the ratio of all the different ratios here. So starting with A here, and this image is from GeoGebra, so if you use that tool, you were able to see that this is how the angles are shown and the side lengths. So with respect to A, here we have 5.9 and divided by sine of 51 degrees. And this is approximately 7.59. Now with B, we have 6.7 divided by sine of 61 degrees. And this is approximately This is also, well, let me round up to 1 decimal point because there are a little bit minor differences. So that's approximately 7.6 there. And C is 7.1 over sine of 68 degrees. And this will be approximately 7.6 here as well. And so the reason I did round is because within this triangle itself, GeoGebra does round up some of these values. So maybe if we were working with 2 decimal points for the side lengths, these were more precise answers. But we can see approximately they are all equal to 7.6, which is what we would have expected from the sine law. And of course, if any of these side lengths were not given to us, we would be able to use sine law to figure out what that last side length is. So with sine law, there are specific cases of when we use sine law. So usually they are represented with these three letters, so AAS, ASA, and SSA. And the order does actually matter. So with AAS, it's angle, angle, side, which means you have two angles and the side that is going to be adjacent to this next angle here. So exactly as it said, one side that's not between them. It could also work this way because then we would have angle, angle, side, just as long as the side is not between them. And in this case, you have, so let's say we are given A, then you have this ratio, and then you can use this ratio between B to solve for that unknown side. Another example or another case is ASA, where now we have angle side angle, which is actually the side that is between the two angles. So in this case, when we have A and C, then the side between them, B, is given to us. And again, here we can use sine law. And I want you to first think for yourself, why can we use sine law in this case? The reason for it is when you have two angles, you can actually solve for this angle, right? Same with here. You technically, as long as you have two angles, you have all three angles because you can use the sum of the interior angles of a triangle, which is 180 degrees, to solve for your last unknown angle. And in this case, given B, I have these two as my ratio that's given, and then I can either solve for C or A, depending on which one I need, and I will use the corresponding angle. And finally, we have side-side angle, where, for example, we have uh, A and B, and the angle opposite to one of those sides. So, for example, here we have A and A. So we have this ratio, and then we can solve for the angle B. And again, once you have this angle B, it's really easy to solve for angle C and then solve for side length C. And so as long as you have the angle opposite to one of the given sides, then you are able to use sine law in this case as well. And so that's why you do have to do the check there to make sure that you actually can apply sine law by having the opposite ratios. So let's solve our first example. So here we are asked to solve for the unknown side lengths. Here we have two adjacent angles and the side length that is not between them. And again, remember, because I have these two, then I automatically have that third side length, or sorry, the third angle measurement as well. So really here, I can do angle C is equal to 180 degrees minus 65 degrees minus 50 degrees, and this is equal to 65 degrees. So in fact, this is actually an isosceles triangle because of these two angles. So we should get that the when we solve for C, that should be equal to 12. So we will check now. So let's start with angle A or side length A. So using, and again, remember now that we have trig ratios, Pythagorean theorem, and sine law, it is a good practice to write which one you're using. So using sine law, A over sine A is equal to B over sine B, which then gives us A over sine of 65 degrees. Actually, yeah, A is what we're trying to solve. And this is equal to 12 over sine of 65 degrees and solving for A. And again, I am skipping my one step here to show that we multiply by sine of 65 there, but sorry, correction. This should be the 50 degrees because it's angle A. Um, and I'll explain why. When we solve for C, you'll see why that makes sense. And here we have 12 sine of 65 times sine of 50. And we have approximately 10.14 centimeters. And I will box this as one of my values. Now, when it comes to C, and this is why, oh, I realized above right away that there was an error there, because as I mentioned, this is an isosceles triangle. So we expect that B and C are equal. And precisely here, if I write C and sine of 65 degrees, which is angle C, and this is equal to B, which is 12 sine of 65 degrees. Now, when I multiply by sine of 65 degrees, that's what I have here. So these two will cancel out. So it will actually become and these two will simplify, and we have C is equal to 12 centimeters, and that's exactly what we were expecting because it is an isosceles triangle, and now I can even label these two as being the same. Now, with these problems where you are solving for the side lengths or unknown angles, you don't necessarily need to write a concluding sentence of, therefore, the side length A is equal to this and sine length C is equal to this. As long as you have your final answer and it is boxed out, that is sufficient, and we will be able to read through your solution. Now, our next example, we are told to find all the interior angles of the following triangle. So here we have two side lengths and we have the angle that's opposite to one of them. So we for sure have one of the ratios. And again, we can use sine law here. So because I have this angle or this side length given to me, I have to solve for angle C first. So it's already written here sine law. So then I will just write A over sine of A is equal to C sine of C. Now, here's also where you can be using the reciprocal, and the reason for that is because I am solving for the angle, so then it saves me a bit of an extra step for rearranging. So I can use this here. So then I can have sine of 45 degrees over 20 is equal to sine of C over 14. So now, from here, I have sine of C is equal to this value here times 14. And really, C is equal to sine inverse of this whole term here. And when I am inputting this in my calculator, and I will show you, I do use that whole expression to get an exact value. So as you can see, and the first bit is cut off, but here we do have um, sine inverse, and then I have my sine of 45 divided by 20, and then times the 14. And if I evaluate this now, I get that angle C is approximately, and with angles, you can always just round to the nearest degree. So in this case, this is 30 degrees because it's 29.7. So then we just round up. And I will box this first. And we are told to find all the interior angles, but now my work is easier because when solving for angle B, I can just use 180 degree minus 30 degrees minus 45 degrees, and this will give me, I think it's 105. Yep, 105 degrees. And then I can box this, or perhaps I write it like this. And then I can just box this one. And I'll erase this here. Okay, there we go. And so there I found my two values. Now again, I will remind you here, if you are using this 30 degrees for the subtraction, keep in mind if you have made an error in solving for this angle, then you are carrying that angle through. So you can always just do a double check with the ratios here to make sure that you still get that same answer. Now, we're asked again to find all the interior angles of this triangle, and it is a little bit different here because we have the exterior angle given to us. But remember that any straight line forms a 180 degree angle. So then if we just do this subtraction here, so I can show here that this is 180 degrees minus 118 degrees is equal to 62 degrees. So I am showing my work there, and then I label it in the diagram there, and that's my work there. So now I have this angle opposite to this side length, and then I can solve for angle N because we have the side length that is opposite to it. So using sine law, and again here, because I am solving for the angle, I'll start with my angles at the top. So sine of 62 over 127 is going to be equal to sine of angle N over 91. So that sine of N is equal to this whole fraction there times 91. And now angle N is sine inverse of the whole thing here. And so angle N is equal to 39. Again, it's 39.25. So then we can just round to the nearest degree. So we say 39 degrees. There we go. And for here, for angle T, we can just do 180 degrees minus 62 degrees minus 39 degrees. And this will be, and in fact, this will be 79 degrees. And one thing to point out here, if you add 79 degrees, so pretty much angle T plus angle N, which are the other two angles compared to 62 degrees, these will actually produce 118 degrees, which is what we saw here. And this again has to do with the sum of the interior angles of the triangle adding up to 180 degrees, but also this straight line adding to 180 degrees. So then these two angles are the same as this angle right here. Now we have here to solve the following triangle. So solving the following triangle means to solve for all the unknown sides and the angles. So this one is a little different now because we have to solve for the unknown sides as well. So we do start by solving for angle A because we have the side length opposite to it. So here we just use the sum of the interior angles of a triangle. So angle A is going to be 180 degrees minus 58 degrees here and minus 42 degrees here, which is 80 degrees. So labeling it here, this is 80 degrees. Now, to solve for the two unknown sides, you can choose either one to start with because now you have one ratio and then you have the other two angles, so you can solve for their opposite sides. So starting with B here, we know that sine or this is side length B and this is side length C. We know that the ratio of B to the sine of 58 degrees is going to be the same as 7.5 to over sine of 80 degrees. So then B is going to be this ratio times sine of 58 degrees, which is 6.5 meters. So this is 6.5 meters. And now we also solve for side length C. It's the same process, but now we use sine of 42 degrees because it's the angle opposite to side length C, and we get 5.1 meters. So here I will label this as 5.1 meters. And a question for you is, why is it recommended to use angle A for both length B and C? So here I did solve for B, 6.5. So why is it still recommended here for me to use the ratio of A instead of using now the ratio of C? And that's what I've been repeating throughout these lessons is anytime you use the values that you calculate yourself, the chance of error is increased. Because if you had made an error here, using that value to solve for another value might mean that you are carrying that error along. However, if you use the values that you are more certain about, because you are solving for angle A here as well, but this is a way easier check than perhaps the sine law used here. So you are more confident about this 80 degrees and the 7.5 that's given to you. So if you use it both times, then your chances of error are lower. And of course, I already did this as I was solving the problem, but if you haven't, label all the solved values on the triangle. Remember, with questions where you are solving for unknown side lengths or unknown angles, you don't really have a concluding statement at the end where you say, okay, the side lengths are all this or the angles are all of these. You could, but it is a little bit redundant to rewrite all of those. But if you label it on your diagram, that's pretty much your concluding statement because now looking at this triangle, this is solved. All the angles are there and all three side lengths are there and labeled. And that was actually our last example for sine law. So pretty much just to recap, sine law is really helpful for us when we don't have right angle triangles in order to solve for the unknown sides and angles. And we are able to use the ratios to solve for either the angle or the side length as long as we have one of these three cases. And in our next class, we are going to see cosine law, which is going to help us when we have the other scenarios of what is given to us. So please complete the practice set below and check Google Classroom for any additional tasks. And as always, don't hesitate to reach out if you have any questions, and I will see you all in our next class.